Right, so welcome everyone to our colloquium this week. Just to recall the general format, during the talk, the audience will be muted. And if you'd like to ask any questions, please just write them into the chat. And either the speaker or I will pick them up. And at the end, we'll have a short question and answer session where anyone can jump in. Otherwise, I'm really happy to welcome our speaker this week, Fei Yan from Rutgers, and Fei is going to tell us about two tales of networks and quantization.
All right, thank you, Tudor. Thank you very much for the invitation to speak here, and thank you for coming to my talk. Today, I will describe two stories of networks and quantization. Just as outlook, so today's talk will be having two parts. Part A will be about construction of a new link invariant, invariant with quotation mark, because it will have some possible wall-crossing behavior for links L in a three-manifold M, where M is a Riemann surface C times a real line. Just some nice properties of this construction. This construction will compute some familiar link invariants in a new way. And it also unifies that computation with a computation of frame BPS indices counting ground states with spin for line defects in 4D=2 series of class S. As we will see, certain networks play an important role in this construction. And although this formulation is for three-manifold taking the form of Riemann surface C times a real line, it is potentially extendable to more general three-manifold M admitting tetrahedron triangulations. And this part of the talk is based on joint work with Andy Netsky. The second part, or part B of the talk, will be about exact WKB method for Schrödinger equations and its higher ordered analogs, which arises as quantization of several written curves in 4D=2 series. Here we will see that similar networks also play an important part in the exact WKB analysis. This part of the talk will be a short review about a recent development plus some new results by myself. And at the end of the talk, I will also very briefly sketch a possibility to bridge these two scenarios based on some discussion with Skelton or Netsky. I should say, feel free to interrupt my talk at any time. So as Tudor said, you could type in the chat and I will try to check the chats in a quasi-periodic way. So let's start with the part A of the talk. This construction happens for the study of line defects in 4D=2 series. Generically speaking, line operators are very important tools in the study of quantum field series. For example, taking a gauge theory as an example, one could have different gauge theories with different gauge groups, which correspond to the same Lie algebra. And those theories could be related to each other by gauging or partial gauging of certain center one-form symmetry. And even for a fixed gauge group, you could get different distinct theories related to the fact that one could make different discrete choices in the gauging of one-form center symmetry. Such distinction is not sensible to the correlation functions or local operators on R4, as those are sensitive only to the Lie algebra. However, such distinction could be captured by the allowed sites of line operators in the theory. So in this sense, line operators capture global structure of quantum field series. And more dramatically, line operators could affect local dynamics of the theory compactified on circle, for the simple reason that wrapping a line on a circle produces you a local operator in the reduced theory. And as another point of view, line defects modeling insertion of infinitely massive particle could tell you information of the back spectrum. And I will briefly return to this point about halfway through my talk. So although it would be nice to directly study line operators in non-supersymmetric theories, and there has been lots of development there, today we're going to study line defects in this 4D=2 series, namely four-dimensional QFT with 8 supercharges. The setup is we consider insertion of a supersymmetric line defect extending along time direction and sitting as the origin of the spatial R3. In Lagrange series, those will be the supersymmetric versions of Wilson-Duft lines. However, there are also generalizations. This kind of object has been studied by many people, both from the more traditional way, and also there will be some more recent work in the context of study of one-form symmetries. So generically, in a generic 4D=2 theory, such a supersymmetric line defect could be not so easy to describe. However, in the special case of abelian gauge series, they are easier to describe, where those line defects could be regarded as word lines of massive BPS dions, namely they're labeled by electromagnetic charge gamma, and moreover by a C-star parameter zeta labeling the preserved supercharges. As a concrete example, take 4D=2 U1 theory and choose an electromagnetic duality frame such that your gamma is purely electric. Then one could explicitly write down the line defect in terms of this kind of form, where this could be regarded as a supersymmetrized version of a abelian Wilson line, where the integral is along time direction, A the U1 gauge field, phi the scalar, are the bosonic field content sitting inside the 4D=2 vector multiplet. So as we said, it's easier to study line defects in abelian series. Could one use this fact to study line defects in more complicated n=2 series? That brings us to the concept of the so-called UVAR map. 4D=2 series have a subspace of vacuum called the Coulomb branch, where at the generic point of the Coulomb branch, the low energy effective field theory is just a abelian gauge theory. So what one could do is start with the supersymmetric line defects in the UV and deform onto the Coulomb branch. And generically, what one will get is not going to be a single line, but generically a superposition of line defects in the effective abelian theory. And this kind of map could be, this kind of procedure could be summarized as a UVAR map for line defects. Here, I have a UV line defect L. This arrow indicates deforming onto a point of Coulomb branch, where one will get a superposition of line defects in terms of infrared Wilson-Duft lines with charge gamma with certain integer coefficient. And those integer coefficients could be understood as certain supersymmetric index counting ground states of this bulk defect system with respect to the charge sector gamma. To properly define this kind of index, we consider the so-called defect Hilbert space, namely the Hilbert space of the theory on R3, where the line defects modifies R3 at a single point. Moreover, you fix a vacuum at infinity to correspond to a point on your Coulomb branch, which is labeled by U here. Such a defect Hilbert space admits decomposition into different superselection sectors labeled by infrared or electromagnetic charge gamma. And within each sector, one could define a supersymmetric index counting the lowest energy states within each sector. So this is the so-called protected spin character, or sometimes also called frame BPS index. And I should say that one could directly count those lowest energy states. However, one could also do a more refined counting. The line defects will preserve SO3 rotation and also preserve SU2R symmetry. So one could use these symmetries to refine this counting of those lowest energy states. And then in general, this protected spin character will take values in some long polynomial in Q. After you take the Q goes to one classical limit, you recover those integers that appear in your UVAR map. As a simple example, if we consider n=2 pure SU2 super Young mills and consider a Wilson line in the fundamental representation, at a point in the wave coupling region, such a Wilson line could be written as a superposition of the three infrared line defects, where here I use a notation gamma E, gamma M to indicate the infrared charges. The first two infrared line defects are not surprising. They're consistent with the semi-classical point of view. Namely, far out into the Coulomb branch, SU2 is broken to U1. So one would expect that the fundamental Wilson line will decompose into those infrared line defects, whose electric charges correspond to the weights of the fundamental representation. However, there's also a third term here, which could be understood as some bound states between this electric Wilson line and some BPS dions. I will not go into details of that, but in generally speaking, the difficulty in figuring out the UVR map is exactly to find those actual surprising terms. And there could be different ways to do this. And today I will give you sort of a geometric way to compute these protected spin characters or the UVR map. And I would restrict, so before all these statements are generically for any 14 equals 2 series. However, when I talk about this geometric construction, I will need to restrict to a large class of 14 equals 2 series, namely the so-called class S series. And such series have a 6C origin. Namely, you could take a 62,0 GLN theory on Riemann surface C times a 4D Minkowski spacetime with some partial topological twisting on C to preserve supersymmetry. After compactification on C, one obtains a 14 equals 2 series of class S. To produce a line defect in class S series, one start with a two-dimensional surface defect in 6D, wrapping the time direction and wrapping some other loop L on the Riemann surface C. After the compactification, then you get a line defect supported along the time direction. So in this way, geometrically speaking, line defects in class S series correspond to loops L on the Riemann surface C. Here I put quotation mark here because generically one would also need to take into account our junctions or the so-called laminations, which is a collection of open paths satisfying certain rules. I will not go into details of those today. When I talk about this line defects, the geometric representation is always going to be this kind of loops on Riemann surface C. And as another remark, the 6D surface defect will carry certain representation of GLN. One quick way to realize that is to compactify the time direction to a circle and reduce on circle. After that, you get 5D equals 2 theory, and the surface defect in 6D are expected to descend to supersymmetric Wilson lines in the 5D equals 2 super-Yang-Mills theory, and which carries a representation of GLN. And today, I will also restrict to just considering fundamental representation. So for class S series, going to the infrared also have a certain geometric meaning. A point on the Coulomb branch corresponds to an n-fold branch covering C tilde over C embedded into cotangent bundle C, which is a Seiberg-Witten curve. In the infrared, the Bach theory could be approximated by the 6D 2,0 abelian theory on C tilde and the 4D Minkowski spacetime. In that infrared theory, one could also take a surface defect, wrap it along some loops on C tilde, and also wrap it along time direction. So in this way, the infrared line defects in 4D correspond to loops L tilde on the Seiberg-Witten curve C tilde. So here I show a schematic picture of this n-fold branch covering C tilde, where with only simple branch point. So in this sense, as we said, the UV line defects correspond to some loops L downstairs in C. The infrared line defects correspond to loops L tilde upstairs on the Seiberg-Witten curve C tilde. So in this sense, the UVIR map for line defects could be geometrically described as a way to lift loops downstairs in C to loops upstairs on the Seiberg-Witten curve C tilde. And this is indeed was developed in the language of the spectral networks by Galton and Netsky. In the following, I will try to describe how to quantize this kind of geometric thinking. But before I do that, I would like to also mention another aspect of this UVR map relevant to the study of Hitchin systems, namely compactified class S series on circle. In low energy, one would get a 3D equals 4 sigma model with target space being a modulus space of solutions to Hitchin's equation. Its Hitchin modulus space is hyperkähler. It has a full CP1 worth of complex structures labeled by theta. As theta equal to 0 or equivalent zeta equals to infinity, the Hitchin modulus space is a complex integrable system. It's fibered over a so-called Hitchin base identified with a 4D Coulomb branch, where the generic fiber are tori, parametrizing the choice of electric magnetic Wilson lines along the circle. For zeta equals to C star, this Hitchin modulus space could be identified as modulus space of flat GLNC connections on the Riemann surface C. So how could one understand line defects in this setup? Consider you have a UV line defects, you wrap it around this circle S1 here. Then after the quantization limit, one would produce a local operator in the 3D includes 4 theory, and its web are expected to be some functions on the Hmodus space. And we could explicitly write down this function as trace or holonomy of this flat complex connection along this little loop L, where we call that L is the loop where you wrap your 6D surface defect to produce a 4D line defect. In this way, this web could be understood as a holomorphic trace function over the modulus space of flat gel NC connections on C. And similarly, you could do the same thing with our infrared line defects. In this way, the web of infrared line defects wrapped around the circle, instead of give you a global function, it gives you certain local double coordinates, which I label as chi gamma here. So in this kind of thinking, this UVLR map for line defects could be interpreted as a trace map, expanding trace of the holonomy of the flat complex connection in terms of the local double coordinates chi gamma with those integer coefficients. As the indices counting lowest energy states lying within each superselection sector labeled by gamma. As we said earlier, it makes sense to define a refined index, is refined by this Fugacity Q here. So this indicates that there should exist a quantization of the UVLR map or equivalent the trace map. To think about how, to motivate how to think about this quantization, I would need to introduce another structure on the space of line defects, namely the line defects operator products. So consider the limit where, recall that line defects inserted at a point in the spatial R3. So you could consider a situation where you have two lines L1, L2 inserted at 2 different points. And then you consider the limit where you bring these 2 points together. Your generic quantum field theory is limited in general singular. However, here, thanks to supersymmetry, its limit is non-singular. And at the collision limit, you get a third line defect denoted as a product of L1 and L2. And moreover, if you think of the web of this product line, it is equal to the product of the web of the individual line defects. So in this way, this line defect OPE is identified with this canonical algebra of holomorphic functions on the Hmodus space. This algebra structure admits a quantization called in terms of the so-called skin algebras, which I will define in the next slides. There are different ways to think about this. I will give you a more geometric, straightforward way to think about this. Namely, recall that I said the line defects correspond to loops on the Riemann surface C. And there is a natural algebra structure on the space of loops on the Riemann surface C given simply by concatenation of loops. And this algebra structure could be quantized if you introduce an ordering of loops. So instead of loops on C, you would be led to consider links on a 3 manifold, which is taking the form of C times a real line. And that's how the skin algebras come into play. Physically, one could also understand this quantization through turning on omega background on a spatial R2 plane. After that, the supersymmetric lines have to be inserted along a fixed axis in R3, which I denoted RH here. Now, if you consider the OPE limit where you bring these 2 lines together, it is still non-singular. However, the 2 limit where you bring L1 to L2 from the left will be different from the limit where you bring L1 to L2 from the right. So in this way, your previous OPE got quantized to be a non-commutative associated OPE labeled by star. In general, this kind of non-commutative product is also difficult to describe. However, in the abelian infrared theory, they're easier to describe. They're given by the so-called quantum torus algebra, which I wrote here. Here on the left-hand side, you're considering OPE of 2 infrared lines with charge gamma 1, gamma 2, and then bring them together. On the right-hand side, you have a single infrared line defect where with charge gamma 1 plus gamma 2, where the infrared charge just adds together. However, there's also an extra piece minuscule to the power of the pairing between gamma 1 and gamma 2, which is a reason for the non-commutativity. And this extra piece takes care of the angular momentum stored in the electromagnetic field sourced by the two dions with charge gamma 1, gamma 2 on the left-hand side. And I should say that this pairing is exactly the Dirac Schwinger-Zwanzig pairing of the infrared charges. So as we said here, one could, both in the UV and in the infrared, one could quantize the line defects OPE, and as a result, the space of line defects are equipped with this kind of non-commutative product. So this hints that if you want a quantum version of UVIR map, it would be a map from this UV skin algebra to the infrared quantum torus algebra. Moreover, this map should preserve OPE on the UV and on the IR, so it should be a homomorphism. Let me see. Okay, so before I talk about this map, let's look at the domain and codomain of this quantum UVIR map, namely the UV and infrared skin algebras. So in the UV, we're considering the so-called GLN Humfley skin algebra associated with the three-manifold M taking form of Riemann surface across a real line. This skin algebra is generated by oriented framed links L inside the three-manifold M up to isotopy and modulo the following skin relations. And skin relations could be understood as relations between different configurations where you only modify your links locally. What do I mean by that? So you literally cut off a little three ball around some neighborhood, for example, of the crossing here, where you keep everything outside the three ball fixed and only modify the details inside the three ball. So for example, the first relation says that on this, the difference between the two configurations where the crossing, the handedness of the crossing has been flipped is equal to Q minus Q inverse times the configuration where the crossing has been resolved. The second relation is a change of framing relation. And I should say that here, in writing down the skin relation, I'm using the standard blackboard framing, or I should say computer screen framing, where the framing vector points out of your computer screen. And the third skin relation says that you could delete this unknown at the cost of this factor here. And similarly, in the infrared, you could also define similar skin algebras. And the skin relations will be more simple looking. For example, you could directly resolve the crossing here at a cost of factor Q or Q inverse. And you could also directly delete an unknown at a cost of identity with no actual factor. However, there's some actual ingredients in the infrared skin algebra. Namely, recall that my separating curve C tilde is a branch covering over the Riemann surface C. And this kind of branching structure will be uplifted to the branching structure of the three-manifold M tilde. Namely, M tilde will be branched over M, where the branch locus will be one-dimensional. If I project this one-dimensional branch locus to the computer screen, it will become a point which are labeled by the orange cross here. And the third skin relation says that pulling a strand across the branch point induces a minus sign here. So that's the reason why I did twisted in front of the GL1 skin algebra. So one could check that this way of defining the infrared skin algebra is indeed isomorphic to the description in terms of quantum torus algebra. And let me also make a remark of what are the objects we're studying here. Namely, I have been telling you that about the line defects which one gets by wrapping surface defect in 6D along some loops on the Riemann surface C in the time direction. However, here I'm talking about links, so it's a different configuration. And this kind of configuration has been studied before, mostly in the context of 3D correspondence. However, I want to study this kind of thing in the 4D setup of class S here. So in particular, if you literally consider a 6D surface defect wrapping along time direction and some links L inside the three-manifold M, you would not get a line defects in 4D because the links will have some finite extent along the RH direction. So you will get some strict. However, if you go to length scale, which is large, such that this finite extent is negligible, effectively you get a line defect. However, this line defects will be different from the the traditional line defects that I talked about at the beginning of the talk, namely it only preserves the U1 rotation and also only preserves the U1R subgroup of the SU2R symmetry. And it preserves less supercharges, namely it is quarter BPS instead of half BPS. And this kind of setup is a key for us to unify this computation of familiar linking variance with the computation of the frame BPS index counting. And one could also recover the more familiar half BPS line defects by taking a link, by considering a subset of such links, which could be isotope to sit at a fixed coordinates along the RH direction. In that way, one would reduce to the more traditional half BPS line defects case. It's because the links will not just traveling along this loop in C, it will also traveling along this RH direction. So it breaks both the SO3 rotation down to U1 and also SU2R symmetry, SO3 early algebra broken to the subgroup U1. I hope that answered the question. Okay, so we'll stop. Okay, so talk about.
Sorry, did you see the question from Greg?
Oh yes, sorry. The question from Greg is the question from Greg.
Oh no, I'm happy to. So he was wondering how the breaking of R symmetry from SU2 to U1 goes.
Right. So it's because I mean this things because R symmetry is like the if you think of the sorry, how should I say? If you think of this because the broken R symmetry is correlated to the broken rotation symmetry, you think in the 60 point of view, because your surface defect will be wrapped around a link, which not only goes just along this, is that, okay, sorry, let me just finish my sentence. Not only goes around the Riemann surface C direction, but also goes around this actual RH direction. So that associated with, there will be an actual SU2R symmetry breaking down to U1 too. I could also make it more explicit if you consider a 60 abelian gauge theory where you could explicitly write down the surface defect as a supersymmetrized version of this holonomial, the B field, which has a self-dual field strength. In that way, you could more explicitly see the broken of the symmetries, and including the preservation of less supersymmetry. Okay, so I've described the domain or codomain of this quantum UVR map. So let me see roughly what does this quantum UVR map do. So concretely, this quantum UVR map sends links L sitting inside a three-manifold M to combinations of links L tilde upstairs in M tilde with some formal Laurent polynomial valued coefficients. And before I tell you the concrete construction, let me just say what the generic picture looks like. So I draw a schematic picture of this three-manifold M, which takes form of Riemann surface across a real line. And then you just put links anywhere in this three-manifold. But I would like to talk about two special limits. And the first limit echoes my comment on the last slide. Namely, you just consider this kind of little loop, which could be isotope to sit at the fixed coordinates along RH direction. For example, this red loop L1 here. In this way, the quantum UVR map will compute for you generating function for the frame BPS indices on this omega, the protected spin characters that we defined at the beginning of the talk for the corresponding half BPS line defects. And if I consider a second kind of special configuration, namely, I just put a small link, where the small means that the neighborhood of link will literally look like R3. And then running the same quantum UVR map algorithm, that will give you this particular one parameter limit of the Helmholtz polynomial. In the n=1 case, this is the Jones polynomial, and the construction reproduces the so-called vertex model studied by Galton and Witten. For n bigger than 2, this construction gives you a new way of computing the higher order analogs of Jones polynomial. And in general, if you consider generic links in here, then the UVR map will compute for your generating function for the protected spin characters or frame BPS indices for this newer quarter BPS line defects in class S theory. And I should say, there's also some other related work which where the by these people where the construction looks completely different. And however, it is believed to us that there should be some sort of relation between our construction with their approach. So now let me just very briefly talk about this construction. And I could summarize the construction using just a single sentence, namely, given a link L in M, I would like to enumerate all possible links L tilde in the covering three manifold M tilde and associate with each lift a long polynomial value factor alpha tilde. And it turns out the second step is very difficult. To motivate our way of approach this problem, let's remind ourselves the physical setup. Maybe going back to 60, and I want to compactify time direction to a circle and reduce on a circle. And one would get a twist state where the twist is a Euro class S twist, and omega deformed 5D equals 2 UN super Young males on M times the R2 plane, where the omega deformation is turned on along the R2 plane. Moreover, I would have a fundamental Wilson line insertion along some links L sitting inside three manifold M. And since we're considering the UVR perspective, the theory is put in a background that generically breaks UN down to UN to the N, where the breaking pattern is labeled by the covering manifold M tilde. And theoretically, what one could do is to expand this partition function of this above setup in terms of partition function of the infrared effective Abelian theory with infrared Wilson line insertions. I put quotation mark expand here because this is not really a well-defined thing in, for example, localization. So to actually carry out the construction this way is difficult. What we did is somehow halfway through, namely we use this physical picture to motivate the ways, the algorithm to enumerate possible links L tilde upstairs. And then we fix those factors using some bootstrap-like method. So let me first talk about the strategies of the enumerating possible links L tilde upstairs. First of all, locally away from branch points, UN is broken to UN to the N. So namely, when when expect the fundamental Wilson line L would correspond to or decomposing to N infrared Wilson lines whose electric charges could be summarized in terms of this following N vector, where each entry corresponds to the charge under the ith U1 group. And there will only be one entry with charge 1, where all the other entries are 0. At the level of links, what it says that if I have a strand of link L away from branch point and away from the corrections I will talk about in the next slides, I could literally uplift this link to this covering three manifold M tilde, where there will be one strand on each sheet of the covering. This picture, of course, cannot be correct in the entirety, as one need to include corrections for massive W bosons, which has been integrated out as one gets to the effective Abelian description. And I will talk a little bit more detail about the what kind of W boson trajectories one should consider, but just summarize what it generically looks like. In the N equals 2 case, the W boson will participate this kind of process in two different ways. A W boson could mediate certain interaction between the Wilson lines with the branch locus where the U2 symmetry is restored, or the W boson could mediate certain charge exchange processes between two Wilson lines. And at the level of operational links, it says if you have a strand of links intersect with certain potential W boson trajectory connected to a branch point, then upstairs, you're allowed to add this little detour term here. And similarly for the exchange process, if you have two link strands L intersect with a single potential W boson trajectory upstairs, you're allowed to add these two little strands running from one link strand to the other link strand. So this is a complete story for N equals 2. For N bigger than 2, the story will be a lot more complicated because W boson will travel along some complicated web structure. So let me briefly describe what are the conditions to find these W boson trajectories. Recall that in the infrared, we're sitting at a point in the Coulomb branch, which is labeled by a separating curve as an n-fold covering C tilde over C. And the separating curve could be interpreted as this algebraic nth order equation, where there are n solutions to this equation correspond to the n sheets of the current. And the W boson has to travel along the so-called BPS leaves, which are one-dimensional leaves on the Riemann surface satisfying this kind of condition. One could understand this condition as a condition that the W bosons have to preserve the supercharges already preserved by the supersymmetric Wilson lines in the n equals 2 super-Yang-Mills series. So what do those BPS leaves look like? In the n equals 2 case, they are simpler to describe. Namely, locally around each branch point, one would have 3 critical BPS leaves emanating from it. And in each 3 region bounded by those critical leaves, there are also generic leaves labeled by this lighter gray color. And globally, these leaves will be either attracted to some punctures on Riemann surface C, where lambda develops a singularity, or it could close up to bound some annulus domain. And this kind of foliation structure will also get uplifted to the 3-manifold C cross a real line. Namely, at each RH coordinate, you will have a copy of this kind of BPS leaf structure from the left-hand side. For n bigger than 2, the situation is a lot more complicated. For example, if n equals 3, then we will have 3 different kinds of BPS leaves or 3 different kinds of foliations. And generically, at a single point on the Riemann surface C, these leaves looks like the following. So for example, you will have JK BPS leaves, you will have IJ BPS leaves, and also IK BPS leaves. And if you look at the neighborhood around, say, a simple branch point where only 2 sheets meet together, then this picture will look similar to the n equals 2 case. Namely, suppose you're looking at the IJ branch point, you will also have these critical IJ leaves and generic IJ leaves. However, there will be many other IK and JK leaves labeled in yellow here going across the region. So it's a lot more complicated. And I should emphasize that even if you're considering the simplest case where you literally take your Riemann surface C to be R2 and C tilde to be trivial covering of R2, namely there's no branching structure or anything like that, the BPS leaves and the potential W boson trajectories are already very complicated. So I could show you some examples, namely I later take my Riemann surface C to be R2, M equals R2 across a real line, and then I take n equals 3, namely I have 3 trivial covering. In this case, I will have 3 different kind of BPS leaves for each slice of this R2 plane. Namely, I have 0, 2, 1, 0, and 1, 2 BPS leaves. And I will show you, one can use a program to find the potential W boson webs. And I show you a picture which is sort of like a chopped up version where I only look at an interval along this real line direction. Namely, my links will be those chopped up link strands colored in blue. And the structure spanned in between those link strands will be the W boson webs. So for example, you could have this web with 3 legs. You could have this web with in total 5 legs and 4 external legs and 1 internal legs. And more interestingly, you could also have a continuous family of W boson webs. So this is indicated here. If you follow my cursor, this red structure here is actually a loop with 6 edges. So this will appear as one of the limit in this continuous family of W boson webs, where the other limit is labeled in blue, given by this tree-like structure. And there's a modulus controlling this continuous family of W boson webs, which could be understood as the length of this little red labeled 2-1 strand here. As one goes from the outer limit of the loop to the inner limit of this tree level thing, this length will shrink to 0. So as you could say, even in the simplest case, the W boson webs could look quite complicated. And I will come back to this factor momentarily. So up until now, I have described to you how to enumerate links upstairs, L tilde, links L tilde upstairs inside the current 3-manifold M tilde. And then what about the factors? So we determine these factors by a bootstrap-like method. Namely, we demand that the quantum UVR map has to preserve the skin relations on both sides, and moreover, it has to be isotope invariant. So for example, the weight factors associated with this kind of web structures could all be determined in a recursive way by certain isotopy moves. Here I show an example where you have 4-link strand with some green W boson web spanned in between. And the isotopy move will be implemented by dragging this link strand L1 towards a point O here. Afterwards, this green web will be killed, and then you get a bunch of other webs with less number of legs. So in this way, those factors could be solved in a recursive way. And we would like to say that there is some pattern of the associated factors with these W boson webs. So of course there will be some prefactors, and I'm not showing you that. However, each of the W boson web is also associated with a factor of Q minus Q inverse to some integer power m, where m is exactly equal to the number of legs minus the number of internal vertices. And it would be nice to be able to interpret this kind of structure of the index as some index counting the ground states for the word volume theory of sorry, I should say that here we're in fact, here we're discussing 5D, and these are the W boson webs. And if you uplift it to 60, those correspond to the trajectories of BPS strings for a 60 series at a point on the tensor branch. So it would be nice to be able to actually interpret this kind of factors in terms of indices counting the ground states of the word volume theory of the BPS string. And I should say, in the case of m equals 1, namely where the W boson is just a simple single exchange strand, this kind of interpretation has already appeared in Galto and Witten. And here the structure seems to say that for each leg, we would want to associate 2 states. And moreover, at each internal vertices, there could be some interactions lifting some of the ground states. And it would be nice to actually prove this kind of statement. So anyway, so after I've described to you roughly this construction of the quantum UVR map, and one could check that this kind of prescription indeed computes this John's polynomial or its higher order analogs. And I'll give you also an example of computational protected spin character in the physical serial SU2 with 4 fundamental flavors. Namely, I take n equals 2. The 3-manifold M is a Riemann surface across a real line, where a Riemann surface is a 4-puncture sphere, where I draw the 4-puncture sphere on the plane, where the punctures are denoted as the blue dots here. And moreover, I look at a link whose projection into C is given by this blue loop. So this corresponds to some half BPS land effects in the SU2 with 4 fundamental flavor theory. And indeed, the quantum UVR map will compute this kind of decomposition of this line in terms of the infrared land effects. And as one could say, in most charge sectors, the lowest energy states are having trivial spin. However, there are also certain sectors where the states form, for example, 2-dimensional representation, or in this case, the direct sum of 1-dimensional and 3-dimensional representation. So up so far, I have talked about this quantum UVR map using a point on the Coulomb branch as a given data. So namely, the quantum UVR map depends on this covering m tilde over n. As I move, are the mu I, sorry, there's a question from Greg, are the mu I flavor charges? I got stuck. Yes, they are. So moving on the Coulomb branch, the frame BPS index or the protected spin character could change discontinuously. This is a so-called frame wall-crossing behavior. And this wall-crossing behavior is controlled by the 4D Buck BPS spectrum. So for example, across the wall corresponding to a BPS hyper, the FLL would jump by this kind of conjugation by quantum dialog. Or so one could check that this algorithm has to respect this kind of jumping behavior. And thinking reversely, by studying FLL before and after the jump, we could obtain the information about the Buck BPS spectrum with spin. This echoes what my comment on the first slides, namely by studying the response of the theory to insertions of land effects, you would get information about the Buck spectrum. So up until so far, I have been focusing on 3-manifold M taking the form of Riemann surface across the real line. However, there are some possibilities to generalize this thing to the more general 3-manifold the mating tetrahedron triangulations. I think I'll skip this point. If anyone is interested, I can come back to it after my talk. So let me just summarize for the part A of the talk. I have described the quantum trace map or quantum UVR map embedding its gel and Hopefully skin algebra into the quantum torus. This gives you a new computational Hopefully polynomial unified with computational refined frame BPS index for line defects in class S series. And it's also interesting to consider more general 3 manifold, and then this will be corresponding to a UVR map for line defects in 3D equals 2 series as a map between the UV and R skin modules. And then as we already seen, certain networks or webs play an important role in the construction. And it turns out a subset of these networks, these also called spectral networks, also appear in a seemingly different setup. And that setup is a study of the Schrodinger equations. So there has been lots of recent development in the study of Schrodinger equations, or I should say the complex Schrodinger equations, where the potential and momentum have been could be taking complex values. So this equation is written as here, where your potential PZ could be holomorphic or meromorphic in Z. This kind of Schrodinger equation also are closely related to 4D equals 2 series, as it could arise as a quantization of separating curve. To see that, we could look at the separating curve of a certain 4D rank 1 equals 2 series, which written as algebraic equation as this, realize that the double cover over surface parameterized by Z. If we think of Y and Z as momentum position, promoting them to Heisenberg operators, in position representations, one will get the following Schrodinger equation. In this way, one could identify a bunch of potentials on the quantum mechanical side with a bunch of 4D equals 2 series. For example, polynomial potential correspond to Algebras series, Matthew potential, modified Matthew potential correspond to pure SU2 superior males. If instead of cosine, you have some other simple polynomials in e to the plus minus iz, that correspond to SU2 with fundamental matter. So there have been lots of people working on this kind of stuff. I should say, as a little warning, which I will not go into detail, there could be subtleties regarding choices or quantization in this case. So a priori, one could imagine one could have two different Schrodinger equations, which reduces in the classical limit to the same separating curve. Or said otherwise, this potential PZ here could have corrections depending on each bar. Then there's a question of whether there's a canonical quantization predicted by the gauge theory. And there are different ways to think about it. I will not go into detail, but to actually motivate this kind of picking canonical quantization, we would need to take a little bit closer look for the relations between 4D equals 2 series and quantum mechanical system. There are at least 3 ways to think about it, and I'll briefly describe each of them. So the first correspondence is the so-called gauge beta correspondence, namely subjecting 4D equals 2 gauge series in the Nekrasov-Shadashvili limit of omega background quantizes the underlying separating integrable system. And to concretely get the quantum separating curve in this way, one could look at the instanton partition function for your theory with the insertion of a certain half BPS surface defect. Such partition function obeys certain vanishing equation, the non-perturbative Dasing-Schwinger equation, which reduces to the quantum separating curve of the Schrodinger equation in the Nekrasov-Shadashvili limit. And work along this line has been developed recently by Nekrasov and collaborators such as Sabyok-Jung and Norton Lee, which I'm sorry I didn't fit as a reference here. Second correspondence is a topological string spectral theory correspondence, which associate a quantum mechanical operator to a toric labial, where the explicit spectrum is computable via topological string free energy. And I should say that here in the original TSSD correspondence, the quantization scheme is with respect to the local mirror curve to the toric labial, where the mirror curve is embedded in C star cross C star. So quantization will actually give you the difference equation instead of differential equation. However, there's a certain 4D limit one could take. Afterwards, you will get the quantum separating curve in 4D equals 2 gauge series. And this has been worked out by Agrassi and Marino and other collaborators. And the third way to relate 4D equals 2 series and quantum mechanical system is the so-called conformal limit. Recall that compactifying class S zero circle at low energy, one will get a 3D equals 4 sigma model with target space being the Hmodus space. And the conformal limit is a special scaling limit of this Hmodus space, namely you take the radius of the compactification goes to 0, and also take zeta goes to 0, where zeta labels a complex structure. but you keep the ratio of those two fixed. That's your H bar parameter. In this way, the H intersection, which is canonically isomorphic to the 40 Coulomb branch, is quantized to the so-called varieties of opers, where for rank 1 theories, the opers are the Schrödinger operators, but in general, they are higher order analogs of Schrödinger-like operators. This kind of conformal limit thinking also allows you to geometrically reformulate exact WKB in terms of so-called abelianization worked out by these people. And I should also say that even before this, there's already geometric way of thinking exact WKB in the community. So it's nice to say that one could actually reach to the similar kind of description by thinking from different point of view. So let's very briefly talk about exact WKB for Schrödinger equations. You make the WKB on that where write the wave function as the exponential of 1 H bar integral lambda. For the wave function to be a solution of the Schrödinger equation, your lambda should obey the following Riccati equation. And as a first step, one could try to build a formal series solution to the Riccati equation in powers of H bar. At order 1, one reproduces the classical Zebra-Witten curve. And there are two choices of solution correspond to the two choices of branch cut, square root branch cut. Once you make this choice, all the higher order in H bar terms are completely fixed. So in the end, you get this kind of formal solution, and you got two of them. Substituting this formal solution back into your WKB on that gives you two formal solutions on set plus minus as a formal series in H bar. Although this is only a formal solution in H bar, in particular, the coefficients diverges factorially, so they're not actual functions in H bar. Given an asymptotic series in H bar where the coefficient diverges factorially, one way to actually produce you a function in H bar is to do the Brar summation. And it turns out you cannot do that globally on the whole Z plane, but you can only do that away from the so-called Stokes curves. So here I draw a simple example of what the Stokes curve looks like. Again, from each branch point, you will have 3 Stokes curves growing out of it, and they are going to be attracted to some punctures or form some annulus, bound some annulus domain. And these Stokes curves will carve out the whole Z plane to different regions, which are labeled as A, B, C, D, E here. Within each region, you could perform Brar summation for this formal solution set plus minus to get 2 actual solutions set plus minus. However, as you cross region, across some Stokes curve separating 2 regions, your actual solution will jump in this kind of unipotent way. So what you get is not a globally defined solution, but also only local solutions in each region, but you also know how to glue them together as you cross the Stokes curve. So that also gives you some sort of analytical control for the actual solutions of the Schrödinger equation. And I should say in the N equals 2 point of view or class S point of view, those Stokes curves correspond to the spectral networks divided by GMN, and it also corresponds to the subset of networks, which I call critical networks, namely networks which connects to branch point in part A of my talk. So I think I'm running out of time, so I'll try to be brief here. So what are some observables you could compute in this quantum mechanical system? Those are so-called Walras symbols, which are C-star valued functions in H bar labeled by infrared charges gamma correspond to 1 cycle of Zebra-Witten curve. There are many nice properties of the Walras symbol. It captures the Brar sum quantum periods, where quantum periods a priori is again some asymptotic series in H bar, defined as integral of the formal solutions to the Riccati equation along some cycle gamma. In particular, at order 1, one would get classical period of the central charge. So the Brar summation and the associated Stokes discontinuities are entirely captured by this chi gamma H bar, the Walras symbol. Secondly, the Walras symbol could be expressed as Wronskins of distinguished local solutions to the Schrödinger equation. And for example, those distinguished local solutions could be the asymptotic decaying solution as Z approaches the singularity, or as eigenvectors of the monodromy around the loop. In this way, the world symbol is identified as spectral coordinates on the moduli space of flat SL2C connections. And roughly speaking, this kind of world symbol could be thought of as the conformal limit of the double coordinates chi gamma zeta on the Hmodus space, which also appeared in part A of the talk in terms of the web of the infrared line defects wrapped around the compactification circle. So let's look at a very simple example, namely the modified mycelial operator, where you have a Koch potential. To make the connection to pure SU2 superior males more explicit, it's convenient to make a sort of change of coordinate from the cylinder coordinates to plane coordinates. And then one could observe that classical Zebra-Witten curve indeed is a double cover over a sphere with two irregular punctures located at z equals 0 and z equals infinity. For real values of H bar, the Stokes curve looks as following. In particular, one sees the appearance of this annulus domain corresponding to the W boson in the n equals 2 SU2 superior males in the weight coupling region. And since it's the rank 1 theory, in this case, we will have two world symbols, chi gamma 1, where gamma 1 is a cycle labeled in blue, and chi gamma 2, where gamma 2 is a cycle labeled in red. The chi gamma 1, chi gamma 2 are the exponentiated Fenton-Nielsen coordinates. In particular, chi gamma 1 is the so-called length coordinates. It is equal to the eigenvalue of the clockwise monodromy around z equals 0, correspond to sheet 1. And chi gamma 2 is the so-called twist coordinates. And as some application, one could consider at what value of E do we have a bound state along the real line, namely a solution which decays exponentially as x goes to plus minus infinity. Or equivalently translated to Z, there will be a bound state solution on the real negative real axis on the Z plane. So this kind of bound states condition is equivalent to say S need to be proportional to T, and which means the twist coordinates should be equal to 1. Since the twist coordinates depend on E, one could reverse this relation to get some conditions on the energy, and therefore this kind of equation sometimes also interpreted as exact quantization condition for the above-mentioned bound states problem. So I mainly talked about world symbols in the context of exact WKB. One could also understand it in terms of 14 equals 2 theory point of view. First of all, the world symbol would obey certain TBA-like integral equation. This kind of integral equation could be regarded as a conformal limit of a different integral equation, played an important role in the study of hyperkilometrics on the Hmodus space. And in particular, as H bar goes to 0, one says that the dominant contribution is given by this term, where Z gamma is a classical period, and this is indeed in line with the WKB on that. And across certain rays in the H bar plane, one says that chi gamma H bar will exhibit certain jumping behavior, and this jumping behavior is completely controlled in terms of the BPS spectrum of the 14 equals 2 theory. As another perspective, incident calculus also computes certain resound quantum periods. Those are the special one, namely the special A and A dual periods corresponding to the special coordinates on the Coulomb branch. They satisfy this sort of quantum special geometry relation, where the generating function for this relation is given by the Nekrasov-Shatashvili free energy. And this kind of free energy, and as a result, A and A dual are going to be a convergent series expansion in terms of the instant counting parameter with a non-zero convergence radius for certain parameter ranges near the semi-classical region. In particular, they're exact in each bar. In this sense, incident calculus also resounds the quantum periods, and they will correspond to some special kind of world symbols, namely the Fenton-Nielsen coordinates or its higher order analogs. And this is in line with this paper by Nekrasov-Shatashvili and also some higher rank generalizations. So I will just say a few words about the higher rank generalization. So far we've been discussing the Schrödinger equations, which is already interesting. And it's even also interesting and challenging to generalize this story to the higher order analogs of Schrödinger equations. And there will be lots of new subtleties here. And in this paper and some work in progress, I'm trying to explore this kind of higher order Schrödinger-like equations from both the exact WKB point of view and the gauge theory point of view, in the context of this third order differential equation arising in the quantization of the n equals to pure SU3 superior Mills theory. So just to give you a flavor, if you look at the strong coupling region, which has 12 BPS states, this is the Stokes curve looks quite complicated. In particular, exact WKB analysis involves analyzing in total 48 local solutions. However, in the end, everything could be expressed in terms of only 2 special solutions, which I denote again as T and S here, where T is the exponential decaying solution as they go to 0 along the negative imaginary axis, and S is the exponential decaying solution as they go to infinity along the negative imaginary axis. So the series rank 2, so there will be 4 Weyl symbols. They could all be expressed in terms of some special, in terms of the about special solutions S and T, and their images under the monodromy, where this monodromy is a monodromy around z equals 0, which has a puncture, and it's taken to be this counterclockwise monodromy. So I'm not showing the expressions. It looks quite complicated, but one could do some classical checks, namely as h bar goes to 0, log of the Weyl symbol is expected to admit an asymptotic series expansion in terms of the quantum periods. And one could do some numerical checks. Namely, on the one hand, one could compute the Weyl symbol in terms of the special solutions. And on the other hand, one could compute the truncated quantum series. And I could say the numerical agreement is relatively good. Moreover, from the gauge theory point of view, one could also compute the Weyl symbol by numerically solving the TBA equation using the data of the 12 BPS states. And the numerical agreement here is not very good. And I hope it could be improved soon. So let me summarize. I described 2 different quantization scenarios. The first one is a quantum UVR map, which gives you a new computational Hopefully polynomial, which is unified with the computational refined frame BPS indices for line defects in class S theory. And the second part of the talk, I described exact WKB method for Schrödinger equations arising as a quantum separating curve of certain 14 equals 2 series. And they both involve certain networks on the Riemann surface C. Then that makes you to ask the question whether there's a possibility to unite these 2 scenarios. For example, one could consider in both of in both stories, one has turned down a half omega background of the Nekrasov-Saakashvili limit of omega background. One could ask whether there's a way to unite these 2 scenarios by turning on the full omega background. And I will not have anything intelligent to say in that direction. I was going to say a different possibility, but I'm running out of time. So I will stop here. If anyone's interested, I could talk a little more about this last slide. Thank you for your attention, and sorry for going over time.
Hey, thank you very much. Let me allow participants to unmute themselves and ask if there are questions. I had one to start. So you talked a little bit about not polynomials or not invariants in the first half. Can you construct something analogous to not invariants using these more general Schrödinger equations?
Yeah, I think so that would be great, but I don't really have a concrete idea of how to do that. You would expect one should be able to do something in this setup of Schrödinger equations of these higher order analogs, but concretely right now, I don't have a good idea.
And is there an interesting interplay with wall crossing? And like the way you define the Hopefully now, it depends on a UVIR map.
Right.
Which can change under wall crossing.
Yes.
Can you say a bit about that?
Yeah. So I didn't say so. Indeed. So in general, if your link is not like small, namely it's not contained inside some neighborhood which looks like R3, you will get this expansion which depends on where you are on the Coulomb branch. So it will have this kind of wall crossing behavior. But if your link is indeed small, then you do not have the wall crossing behavior. And then you could ask, how do I prove that? And I believe, so this is, sorry, I was talking about this kind of setup. If we're considering L2, then there's no wall crossing. You later get this one parameter limit of the Hornfleet polynomial. And for n equals 3 or bigger, I do not have a way to prove it. But for n equals 2, I believe we proved it by considering just by considering the invariance of a construction under a bunch of isotopy moves like random mass moves, and also more general isotopies where, for example, when like, sorry, I need to, for example, when you pull this strand across a branch point, etc. So it involves more isotopy moves, but in n equals 2, one could sort of prove that in the case of L2, your results does not have wall crossing behavior. However, for n equals 3 and higher, I do not have a proof. And
do you actually expect, well, like, do you expect invariance to appear in some interesting way?
Yeah. So,
like,
that's a very interesting question. So, for example, this is like an infrared computation of the UV defined quantities like a Schur index or something. I suppose here you could do something similar, like you take the trace of the generating function combined with this monodromy operator. And because here, this generating function, it jumps in a very similar way, like it literally jumps also by the conjugation by quantum dialog. So I would expect you could possibly construct some sort of invariant by taking the trace of F with the monodromy, the spectrum generator or something. But I didn't really explore that part. Yeah.
Sorry, I didn't mean to monopolize the question session. So there are a bunch of other questions in the chat. Okay. Dennis Sullivan was asking how what the generalization to other three manifolds is.
So drop the slides and stop. Sorry.
Or, Dennis, if you want to just unmute yourself and.
Yeah. You mentioned you might be able to say something after the talk about how you go from surface cross line to general three manifolds. Right.
So I can say a few more here. Sorry, I dropped my slides, but I think that's, but anyway. Right. So I can probably say something about three manifold which admits tetrahedral triangulations. So physically, that setup is going to be a UVR map for line defects in 3D equals 2 series. Namely, one could also imagine to make a perturbation given by some covering three manifold and tilde, and then one could ask, how does the UV line defects in the 3D equals 2 series look like after you make this perturbation? And mathematically, this will be a map, from the GLN scheme module of three manifold M to this twisted GL1 scheme module of the covering three manifold M tilde. Here you do not have the algebra structure because there is no ordering along the real line. So one could imagine, so the key thing would be to figure out what happens within a single tetrahedron for three manifold admitting tetrahedron triangulations. So one could possibly think of the tetrahedron as an interval of this parallelogram, an interval across this parallelogram, where this parallelogram has a triangulation, but the triangulation is flipped as you go from one side of the interval to the other side of the interval. And after you glue together the edges of the parallelogram, you get yourself a tetrahedron. And if your length is located like close to the surface of the tetrahedron, or equivalently close to these two ends, then one could still borrow our construction, namely it looks literally like the parallelogram cross some interval. So one could still have this structure here. So what's difficult is how to glue together these two ends. Like something has to happen in the middle. And in particular, I will not be able to describe in much detail here. This covering three manifold M tilde will have a new kind of singularity, one within each of these tetrahedron. And roughly speaking, that kind of singularity corresponds to the exact moment where this flip of the triangulation happens. So in upstairs, in the twisted GL1 scheme module M tilde, one needs some sort of new, like actual skin relations to take care of this kind of new singularities. But I do not really have much more detail to say because it's still I mean, we haven't really got it working, but that's a rough idea of how to go to the more general three-manifold.
Thank you.
Thank you.
Thanks, Fei. And we'll have the slides on the colloquium website in case they don't get dropped by the end of the meeting.
Oh, I see. That's a good job for me.
If you could, in fact, send them to me or to David Morrison, that would be great. Any other questions?
Hi, Fei.
Hi, Sylvia.
Hi. I was just wondering whether you can say more about turning on full omega background.
Yeah. So the problem is I think I still have some problem of actually setting it up correctly. Sorry, let me think. Yeah, so one could possibly think of like the 4D spacetime as a cigar times R2, where you could have omega background both on the cigar direction and the R2 direction. And then there's a problem of where you put your line operator in that setup. And I imagine one could put a little loop around the cylindrical direction of the cigar. And maybe that is the setup to actually study the thing with both omega background turned on. But I'm not sure. Maybe I think you must know more.
No, I was just asking because, so is it correct that I don't take the conformal limit? It corresponds to.
I was going to say, so one could turn on both omega background, but I'm not sure how to do that. One way is to trade one of the omega background in terms of conformal limit, because as I described in the second story, there are different ways to think of this quantization problem. So you could think of like trading half of the omega background as turning on omega as taking the conformal limit. And then you just need to turn on half of the omega background. So this is the thing I was going to talk about near the end. But in this setup, you don't directly turn on both omega deformation parameter, although you could say the conformal limit is related to turning on half omega background, but I'm not able to actually relate those in all details. But anyway, this is an alternative as turning on the full omega background. Namely, you consider conformal limit, or sort of like you first do not take the conformal limit. Namely, you consider literally consider this kind of a spectral coordinate on the Hmodus space, physically represented as a web of the infrared line defects wrapping around the circle. So the circle which you compactify to get this 3D inverse sigma model with target space being Hmodus space. And there will be an integral equation obeyed by this chi gamma here. And then you turn on half omega background, which quantizes the OPE for this infrared line defects to be the quantum towers. And then you could ask whether there is a Q-deformed version of this integral equation, which is going to be some operator equation respecting these quantum towers. And the jumps consists of a quantum dilogarithm. And mathematically, this could also be formulated as a Q-deformed integral equation which solves a Q-deformed Riemann-Hilbert problem. And it's been studied in some examples in this paper by Barberi, Bridgeland, and Stoppa. And then suppose you have a Q-deformed integral equation pre-conformal limit, then you could consider take conformal limit, then you would get a Q-deformed integral equation for relevant for these Walras symbols. So that's what I meant by maybe you could trade turning on half omega background with the conformal limit. But it would be nice to directly do this turning on the full omega background business, but I still don't have a concrete intelligent way or clear way to say that.
I see. Thanks a lot.
Thank you.
Greg has his hand up too.
Yeah, Greg.
Hi. Yeah, this is a question which is only tangentially related to your talk, but it does bear on some of what you said. So something I've never really understood about quantum Seiberg-Witten curves is you can have very different families of Riemann surfaces
Uh-huh.
with Zeiberg-Witten differential
Right.
define isomorphic special Kähler geometries.
Uh-huh.
For example, just to give one simple example, you could compare the Zeiberg-Witten curves in the paper of Zeiberg and Witten with some of the class S versions.
Mm-hmm.
And they're not isomorphic Riemann surfaces.
Right.
Right. For example, for the SU2 n equals 2 star theory, they had a family of elliptic curves.
Mm-hmm.
But in the class S version, you have a genus 2 double covering of an elliptic curve.
Mm-hmm.
So it looks different.
Mm-hmm.
And so my problem is that, okay, supposing I have two different families of Zeiberg-Witten curves and differentials that define isomorphic special Kähler geometries.
Mm-hmm.
A priori, you would think that the quantizations, even putting aside the ordering problems that you alluded to, a priori, it's really not obvious that those kinds of quantizations, the quantizations of these curves would have anything to do with each other.
Exactly, you're absolutely right. So
I was just wondering if anybody takes that point seriously.
I take that point seriously, but I didn't mention this. So sorry. Sorry. One thing I didn't mention is this pure SU3. Sorry, this quantum curve for the pure SU3. I am using the class S realization for the classical curve, which is like a threefold covering over a sphere with two irregular punctures located at z equals 0 and z equals infinity. However, as everyone knows, there is a different classical curve, which is sort of like a hyperelliptic curve, describing not just SU3, but SUN generically. And if you quantize that curve, you will get some sort of like a deformed quantum mechanics problem. So instead of P squared, you get cos P, but then you get some potential. So that kind of problem has already been studied by Garcia and Marino, and from the gauge theory point of view. And as you said, a priori they're different things. So there you get this deformed quantum mechanics model, and here you get this third order differential equation. And okay. I don't.
Yes, that's a very nice example of what I was talking about. So I mean, do you expect that there's going to be some kind of isomorphism between these?
So in terms of isomorphism, I do not have like a mathematical way of isomorphism or anything, but I do expect, which I'm still checking. So I do expect, for example, the computational quantum periods should match because physically they correspond to the same.
Well, right. Ultimately, the chi gammas should be the same.
Yes. But I do not have like a mathematical way to say why this chi gamma would even be the same.
Okay.
For one thing, the gauge theory actually only computes some special chi gamma, these Finchel-Nielsen or higher rank analog. So there will be some subtleties there, but
in case people don't want to disconnect this seminar, may I comment on Greg's question?
Yes, please.
Right. So, Greg, there are two different questions you can ask, right? One is you have this Hitchin integrable system, which is defined classically, and you can ask, can we quantize it? And another is relation of this quantization of Hitchin integrable system to quantization of spectral curve. I mean, this first question, quantizing Hitchin system, is slightly better, right? You have a set of commuting Hamiltonians, you're asking to find the spectrum and eigenvalues. Now, somehow it happens that in some cases, these two questions, quantizing curve and quantizing Hitchin integrable system, look the same, but they're not the same. They are related, but not the same.
I see.
Right? Is not? Am I right? I want to hear what Greg thinks about it. So,
well, I think this is another aspect of the whole. What I find so bewildering about quantum Zeiberg-Witten curves.
Right. So let's put aside quantum Zeiberg-Witten curve and ask question: can we quantize Hitchin Hamiltonians, which are given as a coefficient?
That's also a well-defined problem. I agree.
Okay, so now if we answer that question, right, somehow, Then we can ask how it relates to quantization of carbon. I think that's what Marcus was doing all this time.
Ah, okay. I see. Okay.
So he would take, let's say, we would produce this deformed prepotential, right? One epsilon deformed prepotential. And then he would say, okay, let me take this, whatever, one parameter deformed prepotential, and now ask the question, how does it help me to quantize the curve and then relate to topological strengths? And he had, he had some very nice formulas about it. Now, what Greg is asking is that these curves can be different, but it's describing same system. I think what Marcus would say is that yes, curves would be different, but the deformed one parameter deformed prepotential from gauge theory is given. It's the same one. Okay, so now his formula would produce out of this my prepotential with Nikita would produce the answer to the quantization of both curves, and then probably he can compare. I don't know, but I just want to hear that Greg agrees that the quantization of Hitchin system is slightly better posed question.
Right. So thank you very
That
much.
sounds right. That sounds right. Yeah.
Okay, that just was a comment. Sorry, I didn't want to interrupt your seminar.
Thanks a lot.
Thanks.
Yeah. Yes. So one should be able to compare. Yeah. Thanks a lot.
Right. Let me just ask if there are any other questions, and if there's further discussion, we can keep going. But I'll stop the recording.
Thanks.
Okay. Well, let's all thank Fei again, and thanks everyone.
Thank you.
Yeah, it was really a pleasure. Thank you.
Thank you for the invitation.
Yeah. Okay. And then we'll see everyone in 2 weeks.
All right. Thanks a lot. Bye.